Hi, I'm Cameron from Minute Earth, and I'm about to show you some videos that will tell you pretty much everything you ever wanted to know about solar eclipses. But first, I want to talk about my shirt. This shirt shows what solar eclipses might look like from the surface of other planets in our solar system. And to get your own, go to our store at dftba.com/MinuteEarth. A few years ago, I got to see something spectacular. It was a total solar eclipse, and it was nothing like I expected. Ever since then, I've been completely fascinated by solar eclipses. So when the folks at NASA's Heliophysics Education Activation Team reached out to us at Minute Earth, as well as Henry at Minute Physics and Jasper over at Minute Labs, to make a bunch of videos and an interactive about solar eclipses, you could say I was over the moon about it. First, I dug into the history of eclipses, and I found that eclipses have been regarded as terrifying omens almost as long as humans have been around to see them.
These days, we know exactly when eclipses are going to happen, and we even look forward to them. But humans didn't learn to predict eclipses because they were exciting. It was because long ago, eclipses were terrifying. Hi, I'm Cameron, and this is Minute Earth. For people living thousands of years ago, the sun suddenly vanishing from the sky was a pretty alarming experience. Even the Chinese word for eclipse literally means to eat, as in the sun is being eaten by a dragon. So it's no wonder that ancient people came up with all sorts of different explanations for both solar and lunar eclipses and tried to understand when they might happen again. About 5,000 years ago, people in what is now England lugged about 100 massive stones through the countryside to build a structure we now call Stonehenge. It's mostly composed of an inner ring of large stones and an outer ring of smaller stones, and if you stand in the center of the rings, the sun appears to rise behind this stone on the summer solstice, which shows that Stonehenge was built for watching the sky. There is also a ring of 56 post holes surrounding the monument that, by moving posts from hole to hole around the circle to track the positions of the sun and moon, could theoretically have been used to track the timing of lunar eclipses, but Stonehenge's builders didn't leave behind an instruction manual, so scientists still have a lot of questions about what the builders' intentions were. 4,000 years ago, Chinese astronomers made the oldest suspected mention of an eclipse. It was the first of roughly 920 solar eclipse accounts appearing throughout Chinese history. However, most of the early descriptions were too vague for modern astronomers to pinpoint exactly when they happened. The earliest verifiable eclipse sighting was recorded on a 3,300-year-old clay tablet that describes a total solar eclipse that was seen in the city of Ugarit in modern-day Syria in 1223 BCE. Nearly 600 years later, in nearby Babylon, eclipse watchers would finally figure out the pattern that eclipses follow. Lunar eclipses, that is, when a full moon completely enters the Earth's shadow and turns red, were of great interest to the Babylonians because Babylonians saw lunar eclipses as bad omens for their kings. And it turns out that lunar eclipses were the key to spotting eclipse patterns. When the moon passes into the Earth's shadow to create a lunar eclipse, the event can be seen from the entire nighttime half of the planet. When the moon casts its shadow on the Earth during a solar eclipse, the eclipse can only be seen from within the moon's shadow. So astronomers in Babylon would see roughly half of the lunar eclipses that happened, as opposed to only a handful of solar eclipses. That gave the astronomers enough data to figure out that lunar eclipses seem to repeat every 18 years, 11 days, and 8 hours, a pattern which we now call the Saros. And it turns out that the Saros also applies to solar eclipses. If a solar eclipse happens here, another one with a similar path will be visible 18 years, 11 days, and 8 hours later. However, because of those extra 8 hours, the Earth will have rotated 120 degrees farther around, and the eclipse path will be shifted 120 degrees westward of the last one. And the same goes for the next eclipse in the cycle, and the next, and the next, and you get the idea. For example, these are the similar paths of one repeating set of solar eclipses during the 20th and 21st centuries. Of course, both solar and lunar eclipses happen more frequently than every 18 years. That's because as many as 40 different sets of identical eclipses are overlapping at any given time. These days, we can not only calculate the timing and path of every eclipse that has occurred over the last 4,000 years, we can also accurately predict them far into the future. Like the solar eclipse that will happen on September 7th, 2974, that at 12:51 p.m. local time will pass right over Stonehenge.
Eclipses used to be so terrifying because, at least in part, they happen so rarely. But again, that led to even more questions like, If the moon orbits the Earth once a month, then why don't we get solar eclipses once a month? Turns out, I'm not the only one to wonder.
The moon orbits the Earth once per month, which means the moon is on the sun side of the Earth every month. So why aren't there eclipses every month is a question answered eloquently in a 1757 astronomy book by James Ferguson. It's kind of the 18th century equivalent of Astronomy for Dummies, complete with amazing illustrations. Here's Ferguson's surprisingly good 250-year-old explanation for why there aren't eclipses every month, illustrated by me. Every planet and satellite is illuminated by the sun, and casts a shadow towards that point of the heavens which is opposite to the sun. When the sun's light is so intercepted by the moon that to any place of the Earth the sun appears partly or wholly covered, he is said to undergo an eclipse, though properly speaking, 'tis only an eclipse of that part of the Earth where the moon's shadow falls. When the sun is eclipsed to us, the moon's inhabitants on the side next to the Earth, if any such there be, see her shadow like a dark spot traveling over the Earth, about twice as fast as its equatorial parts move, and the same way as they move. If the moon's orbit were coincident with the plane of the ecliptic, in which the Earth always moves, the moon's shadow would fall upon the Earth at every new moon, and eclipse the sun to some parts of the Earth. But one half of the moon's orbit is elevated 5 degrees above the ecliptic, and the other half is much depressed below it. Consequently, the moon's orbit intersects the ecliptic in two opposite points, called the moon's nodes. When these points are in a line with the sun at new or full moon, the sun, moon, and Earth are all in a line, and if the moon be then new, her shadow falls upon the Earth. If full, the Earth's shadow falls upon her. When the moon is more than 17 degrees from either of the nodes at a new moon, the moon is then too high or too low in her orbit to cast any part of her shadow upon the Earth. But when the moon is less than 17 degrees from either node at the time of conjunction, her shadow falls upon the Earth. The moon's orbit contains 360 degrees, of which 17 degrees, the limit of solar eclipses on either side of the nodes, is but a small portion. And as the sun passes by the nodes but twice in a year, it is no wonder that we have so many new moons without eclipses.
All of this eclipse talk is probably getting you pretty excited to see a total solar eclipse. And if so, I've got some good news for you. Every year, there are at least 2 total solar eclipses that occur somewhere on our planet, so maybe the next one will happen near you. I should warn you though, your odds of living close to the next eclipse, or even the one after, depends entirely on your latitude. Every location on Earth has been in the shadow of at least one total eclipse, but some places experience way more of these events than others. Like, someone who lives north of the equator is about twice as likely to see a total eclipse as someone south of the equator. Why on earth would that be? Hi, I'm Cameron, and this is Minute Earth. This disparity in total eclipses can only happen because of a celestial coincidence. Although the sun is 400 times bigger than the moon, it's also 400 times farther away from us. So as a result, from here on Earth, the sun and moon appear to be almost exactly the same size. I say almost because the Earth's orbit around the sun is not perfectly circular. During some parts of the year, the Earth is a little farther away from the sun, so the sun appears slightly smaller than usual. During these times, when the Earth, moon, and sun line up, it's easier for the moon to effectively block the sun, causing a total eclipse. But other times of the year, the Earth is closer to the sun, so the sun appears larger than normal. When the Earth, moon, and sun line up during these times of the year, the sun appears larger and the moon might not totally block it, creating an annular eclipse, which is when the moon turns the sun into a bright ring of fire in the sky. And here's where the north-south divide fits in. In either hemisphere, eclipses are more likely in the summer, when the sun spends more time above the horizon, since it has to be daytime in order to see a solar eclipse. And it just so happens that summer in the northern hemisphere happens at the farthest out point of Earth's orbit, while summer in the southern hemisphere happens at the closest point of the Earth's orbit. As a result, total eclipses are more likely to happen north of the equator. For any given spot in the northern hemisphere, a total eclipse happens on average once every 330 years. In the southern hemisphere, it's more like once every 550 years. But even within the northern hemisphere, total eclipses become more frequent with higher latitudes. There are a few different reasons why this might be. For one, at the highest latitudes, the summer sun rarely dips below the horizon, meaning that there is sunlight even at nighttime, as opposed to lower latitudes where nighttime is dark during the summer. Then there's the curvature of the Earth, which causes the moon's shadow to fall at a shallower angle at higher latitudes. Eclipse paths near the Arctic Circle can be more than 4 times wider than eclipses at lower latitudes. So statistically, the best place to see a total eclipse is around 80 degrees north, Any given place around this line sees a total eclipse every 238 years on average. But remember, all of these numbers are averages taken over a long period of time. Carbondale, Illinois, which sits at 38 degrees north latitude, which should see a total eclipse every 330 years on average, saw its most recent total eclipse in 2017, yet will get its next one in 2024. And Christchurch, New Zealand, which should get a total eclipse once every 420 years, saw its most recent total eclipse nearly 2,000 years ago, and will have to wait nearly another 4 centuries for its next one. So when it comes to seeing a total eclipse, it's not just about latitude, it's also a matter of luck. Total eclipses might happen somewhat unevenly or seemingly randomly across the Earth's landscape, and some places can get super lucky with them while others can seem pretty left out. But there is one thing you can pretty much always count on, and that is that eclipses will travel from west to east across the landscape for the most part, which is super weird, isn't it? Because both the sun and the moon travel east to west.
The sun rises in the east, the moon rises in the east, and the stars rise in the east. But solar eclipses oddly come from the west, like the April 2024 North American eclipse or the August 2027 North African eclipse. Except not all total eclipses come from the west. A few near the north and south poles actually head west for a bit before turning around and then heading east, which seems weird. If eclipses are caused by the sun and the moon, why don't they behave like the sun and the moon? The key to the explanation is that the paths of the sun and moon through the sky depend on the rotational speed of the objects involved, while the paths of eclipses depend on just the plain old straight line speed of the moon above the Earth's surface. Viewed from the North Pole, the Earth and moon both rotate counterclockwise, that is, towards the east. The path of the moon through the sky is determined by the line of sight from the Earth's surface to the moon, and because the Earth is rotating faster than the moon is orbiting, the sight line and the moon starts off pointing to the east at moonrise, then as the Earth rotates, the moon appears to pass overhead and set in the west, even though the moon is traveling towards the east the whole time. In contrast, the path of an eclipse is determined not by the direction from us to the moon, but by where the moon's shadow falls on the Earth's surface, and the moon's shadow just points away from the sun. The moon is traveling eastwards around the Earth at just over 2,000 miles per hour, and its shadow travels at basically the same speed, eastwards at just over 2,000 miles per hour. The Earth's surface is also moving to the east, but not nearly as quickly. The surface at the equator is only moving around 1,000 miles per hour, and slower the closer you get to the poles. Also, the parts of the Earth experiencing sunrise and sunset are moving mostly towards the moon or away from the moon rather than parallel to its motion, and so they're effectively moving 0 rather than 1,000 miles per hour. The point is, regardless of where you are on Earth, the moon's shadow easily outpaces the Earth's surface's eastward motion, which means eclipses appear to move from west to east. Put another way, the face of the Earth is about 8,000 miles across, so the moon and its shadow cross the Earth in around 3.5 hours, and less near the poles, while any point on the Earth takes 12 hours to cross the Earth. It takes half a day to rotate halfway around the Earth. It's kind of weird that the moon can orbit slower than the Earth rotates, but travel faster. But the moon has a long way to travel, nearly 1.5 million miles over its month-long orbit, which equates to around 2,000 miles per hour. In contrast, a point on the equator only travels 25,000 miles each day, which gives 1,000 miles per hour. There's no cosmic reason that eclipses on Earth travel west to east. It's essentially just a coincidence. If the Earth were twice as big or the moon were half as far away, then the length of a month or day wouldn't change, and neither would the direction of moonrise, but the relative linear speeds of the surface of the Earth and the moon would change, and eclipses might move from east to west. In fact, if the Earth and moon's sizes were adjusted so that the moon was traveling slower than the Earth's surface at noon, but faster at other times of the day, it would be possible for an eclipse to move east, then west, then east again. Geometry is weird. Speaking of weird, those weird west-moving eclipses near the poles happen because the Earth's axis of rotation is tilted, so it's possible for the moon's shadow to be moving to the east, but hitting part of the Earth on the nighttime side of the planet. You can get a rough idea by opening up Google Earth and drawing a bunch of straight west to east arrows across the Earth to represent eclipse paths. If you look at these arrows from another vantage point, oops, suddenly the eclipse paths look way more wonky and some of them go backwards. And while we're in Google Earth, if you tilt the Earth like it is during the spring and fall and draw some horizontal lines, you can get a sense of why eclipse paths follow the curvy shapes they do, though actual eclipse paths are more complicated because the Earth is also rotating at the same time. In summary, even though the moon orbits to the east slower than the Earth rotates in the sense that a month is longer than a day, the moon also orbits to the east faster than the Earth in the sense that the moon is literally traveling through space at a faster eastward speed than the surface of the Earth. And that is what determines the direction of an eclipse.
So as the eclipse I got to see passed from the west coast of the US to the east, it passed over much more than just us eager humans. It also passed over tons of wild animals who I can only assume were caught totally unaware. And that's something I had firsthand experience with when I was in the darkness of totality myself. The animals around me pretty much just freaked out, which of course made me super curious about what they might have been thinking.
When I saw my first total solar eclipse in 2017, I noticed something strange, like, other than the sun going dark. All the songbirds around suddenly landed in trees and started singing en masse. But I'm far from the first to notice animals doing weird stuff during an eclipse. Almost 600 years ago, an astronomer noted that birds fell down from the sky in terror of such horrid darkness. More recently, there was a report that a group of Galapagos tortoises huddled together during totality, then half of the group started mating before they all gazed upward at the sky. So, what do we actually know about how animals experience solar eclipses? Hi, I'm Cameron, and this is Minute Earth. Hundreds of anecdotal accounts of animals' weird eclipse-related behavior exist, going back hundreds of years. Academia is interested too. The roughly 2 minutes of totality during the 2017 eclipse across North America alone generated at least 26 scientific papers on the topic. And at first glance, it seems like we can pretty easily sort animals' reactions into various categories. Some behaviors are freakouts that seem related to anxiety, like the baboons who paced their zoo enclosure, or the horses who clustered together and shook their heads and tails, or the giraffes that ran frantically in circles. Then there are the nighttime behaviors. Birds fly back to their roosts, nocturnal bullfrogs leave their daytime hidey holes, and orb-weaving spiders, who normally build new webs every day, are tricked into dismantling their webs once the darkness of an eclipse hits. Then there are the completely novel behaviors. In one study, a group of gibbons started making strange calls the researchers hadn't heard before, and a troop of chimpanzees reportedly climbed into trees to gaze at the sky. And some animals don't seem to react at all. But when you start really looking at what we actually know, things start getting a little messy. First, there's the issue of sample size. Total solar eclipses only occur about once every 18 months, and each one only covers a small swath of the planet at a time. As a result, specific places can go more than 100 years between eclipse experiences, making repeated observations of animals in the same habitat challenging, to say the least. So it's not surprising that some studies completely contradict each other, like this one, which found that black-crowned night herons make a ton of possibly anxious noise during an eclipse, and this one, which says that black-crowned night herons stay silent during an eclipse. So it's super hard to know how to categorize their behavior. Second, it's really hard to know what's going on in an animal's head, especially without repeated observations and controlled experiments. So we can't possibly know why, for instance, those tortoises were compelled to mate during the eclipse. And that brings us to the issue of, well, us. We are primed to expect that animals might do something weird during an eclipse, and these expectations might lead even the most careful observers to interpret whatever an animal does during a solar eclipse as being caused by the eclipse itself. In fact, all of these anecdotes and research may teach us more about ourselves and how profoundly eclipses affect us than about what exactly animals are doing or thinking during those 2 minutes of totality. Eclipses can invoke fear and anxiety, or excitement and wonder in our own species, so perhaps it's natural to expect, or even hope, that other creatures are sharing a piece of that experience with us.
I suppose there's something innately fascinating about the way that both human and wild animals freak out during eclipses, but there are also some tangible benefits to our intense interest in eclipses. Because we're obsessed with them, we pay attention to them, and we study them, and we've done some pretty cool science from within the moon's shadow.
Solar eclipses are amazing and awe-inspiring phenomena, and they've also been great for science. Hi, I'm Cameron, and this is Minute Earth. Solar eclipses are intriguing and remarkable, so even ancient civilizations were careful to write them down when they happened. This means we have lots of detailed eclipse records from throughout history. Many years of studying eclipses taught us that they occur in a very predictable pattern, which is so consistent that we can extend it both into the future and into the past to predict and retrodict solar eclipse events. When scientists use computer models to rewind the movements of the Earth and Moon, they predict that an eclipse should have been seen along this path in 136 BCE. But this tablet suggests that an eclipse was seen at the same time, but thousands of miles away in the city of Babylon. From this and other eclipse records, scientists noticed that the farther back in time they went, the further off their predictions were. From that, scientists concluded that the Earth's spin is slowing down over time. Modern astronomers had suspected that the moon's gravitational pull, the same pull that creates the tides, was slowing down our planet's spin, making our days longer. But eclipse data told us precisely how much the Earth is slowing down. The length of a day increases by 1.8 milliseconds per century. And this wasn't the only time eclipses had a hand in a big discovery. Scientists used eclipse observations to confirm Einstein's theory of general relativity, which predicts that massive objects have so much gravity that they noticeably bend beams of light that pass by them. Einstein's theory predicts that an object the size of the sun should produce a considerable bend, causing stars appearing near it to show up in slightly different positions than normal. To test this theory, astronomers took a photo of the sun during the totality of an eclipse, when stars appeared next to it. When they overlaid another photo of the same stars taken at night, they found that some of the stars had indeed shifted their apparent positions. This helped establish general relativity and laid the groundwork for us to have nice things like GPS on our phones. On a lighter note, eclipses also helped us discover helium. In 1868, an astronomer named Jules Janssen was interested in the sun's corona, the super hot layer of plasma surrounding the sun. The corona emits its own light, and Janssen knew that if he could analyze that light, he could figure out the corona's chemical composition. At the time, the corona was impossible to see under normal conditions because the rest of the sun was just so much brighter, and there was no way to block out that light. Again, an eclipse was the answer. In fact, that ring visible during a total eclipse is the sun's corona. By analyzing the wavelengths of light coming from the corona, Janssen and his colleague Norman Lockyer were able to identify the individual elements that make up the corona, including one previously unknown element, helium. Eclipse science goes beyond just those examples. We've used eclipses to study how the sun's corona creates solar winds, and how those solar winds affect the Earth's atmosphere. So eclipses are beautiful and awe-inspiring phenomena, and they've also brought some amazing science to light by darkening the sky.
Hopefully I've been able to convince you that total eclipses are awesome events that you should really try to go see if you're able to. And I don't mean to pressure you, but time is running out. We're all super lucky to be alive during Earth's golden age of eclipses.
We are in the golden age of solar eclipses, but only for the moment. In fact, I'd argue we're already past peak solar eclipse and it's all downhill from here. Let me explain. Solar eclipses are amazing phenomena, but they're also just like one object casting a shadow on another, which we see all the time. I think we're impressed by our current solar eclipses for a few key reasons. First, and obviously, they block the sun in the middle of the day so it gets dark, cold, you can see stars, etc. Second, our eclipses aren't purely like night either. The shadow of the moon is small enough that there's still sunlight falling on the atmosphere near the horizon, resulting in a deep blue sky and the appearance of a sunrise or sunset 360 degrees around you. Third, our current eclipses also reveal the sun's corona, the outer part of the sun's atmosphere that's much dimmer than the sun's bright disk and normally lost in the sun's glare. But when the sun's disk is covered during an eclipse, the corona appears like a bright starburst around the dark disk of the moon. Fourth, total eclipses are rare. Any given point on Earth only experiences about one total solar eclipse every several hundred years, so they're kind of a once-in-a-lifetime or less experience. Fifth, eclipses are fleeting. Totality typically only lasts a few minutes, which makes them feel even more precious and cosmic, and also doesn't give our human brains time to really process or take in the weirdness of what's happening before it's over. And finally, eclipses on Earth are also notable because they can be either total, where the moon fully blocks the sun and is spectacular, or annular, where the moon appears smaller than the sun and never completely obscures it. At best, there's still a ring, or annulus, of the sun visible, hence annular eclipse. Because they don't fully block the sun's disk, annular eclipses aren't really much more impressive than partial eclipses. The sky doesn't get deep blue, you don't see the corona, you can't look at them with your naked eyes, etc. They're cool, but are nothing like a total eclipse. It's kind of weird that we have both annular eclipses, where the moon appears smaller than the sun, and total eclipses, where the moon appears bigger than the sun. That both happen is due to the fact that the Earth and the moon's orbits aren't perfectly round, so the relative distances to the moon and sun change over time, and therefore so do their relative apparent sizes. But here's a sad fact. We have on average more annular eclipses than total eclipses. And that is why we are currently past the peak of the Earth's golden age of eclipses. The moon formed billions of years ago, and we have good reason to believe it was much closer to the Earth then than it is now. With the moon so close, it was much bigger in the sky. Total eclipses would have been much more common and much longer and much darker. The moon's shadow would be so big that an eclipse would be much more like normal nighttime, rather than a deep blue sky with golden glow all around the horizon. The moon would also have been big enough to cover most of the sun's corona, and the moon would have been more illuminated with Earthshine, meaning a solar eclipse would probably feel kind of like a normal night sky, just with a darker than normal moon. Boring. However, for all the billions of years after the moon formed, the Earth was spinning faster than the moon was orbiting, as it still does. A day is shorter than a month. And so over time, tidal forces have transferred some of the Earth's rotational momentum to the moon, sending the moon farther and farther away. Up until around 700 million years ago, the moon was close enough to the Earth that it always appeared larger than the sun, and we only ever saw total solar eclipses. But around then, the moon finally moved far enough away from us that, at least during certain parts of the Earth's and moon's orbits, the moon appeared smaller than the sun in the sky. And if it appeared smaller than the sun during an eclipse, it wouldn't fully block the sun. You'd get an annular eclipse, not a total one. Initially, most eclipses would still have been total solar eclipses, with annular eclipses being rare, but as the moon continued to get farther and farther from Earth, annular eclipses became more and more common. Sometime in the last several hundred million years, we crossed a threshold to where the moon appears smaller than the sun on average. At that point, annular eclipses became more common than total eclipses. Fast forward to today, and there are around 20% more annular eclipses than total eclipses. And as the tides continue to transfer our angular momentum to the moon will continue to get farther from the Earth, annular eclipses will become more and more common, and total eclipses rarer and rarer. Until around 500 million to billion years from now, the last total solar eclipse will darken the sky on Earth, and the golden age of eclipses will be over. Let's hope it isn't cloudy.
Now that you know pretty much everything there is to know about eclipses, it's time to start playing around with them. Over at Minute Labs, Jasper and the gang have spent the last year creating the best Eclipse interactive in the entire solar system. In the lab, you can simulate a solar eclipse here on Earth, or any other planet that has a moon. Watch Mars be eclipsed by its lumpy potato moon Phobos, just like on our shirt. Or see the rings of Saturn revealed as Titan blocks out the sun. We've worked with NASA experts to get the atmospheres, orbits, and everything else as scientifically accurate as possible. This interactive is truly out of this world. Oof. Who writes this stuff? Oh, right, me. Anyway, go check it out at minutelabs.io/eclipses, or simply click the link in the description.